Hello everyone, welcome to my channel. I'm M.DAMALIE. In today's rapidly evolving digital landscape, mastering AI is not just a perk, it's an imperative. As I present this course, my goal is to empower each one of you to harness AI's potential. Together we'll delve into its transformative power to innovate, solve complex issues, and foster seamless team collaborations. I'm here to guide you through this journey, ensuring that you're not just observing the AI revolution but actively participating in it. Let's embark on this enlightening path together and shape the future. Ready to be a part of this AI journey? Before we begin, don't forget to hit that like button and subscribe for more enlightening content. Machine learning, ML, is a subset of artificial intelligence, AI, that involves the use of algorithms and statistical models to allow computers to perform a task without using explicit instructions. Instead, they rely on patterns and inference. It's about building systems that can learn from data rather than following predefined rules. Example, imagine an email spam filter. Instead of manually defining rules to detect spam emails that contain the words lottery or free money, machine learning allows the filter to learn and identify spam characteristics from large amounts of labeled data, emails marked as spam or not spam. Over time, as it processes more emails and receives feedback, the filter gets better and more accurate in distinguishing spam from legitimate emails. This self-improvement is the essence of machine learning. When we talk about traditional software, we're referring to systems built on explicit instructions hand-coded by developers. Think of them as following a strict recipe. In contrast, machine learning isn't tied to such explicit directions. Instead, it learns from vast amounts of data, evolving and adapting. So, while traditional software excels at rule-based tasks, machine learning shines when the rules are murky or undefined, and when errors pop up. In traditional setups, it's likely a code glitch. But with ML, it might be the data itself or how the model was trained. In essence, traditional software is like following a map, while ML is more about charting new territories based on past journeys. What is a model? A model in machine learning is a mathematical structure trained on data to make predictions or decisions. Examples: linear regression predicts values like house prices from features. Decision trees categorizes items such as classifying emails as spam. Neural networks recognizes patterns often used in image recognition. Support vector machines classifies items such as identifying tumor types. K-means groups similar items like customer segmentation. Reinforcement learning learns through trial and error, e.g., robot navigation. A model essentially provides solutions based on past data. Let's kick things off with selected features. At its heart, machine learning is about using data to make informed decisions. But not all data is created equal. Think of it as picking ingredients for a gourmet dish. The choice between fresh basil and dried basil can make all the difference. In the world of machine learning, we choose the most relevant pieces of data that can best help our model. Consider a Tesla car's self-driving feature. It needs to know the distance to the car in front, the speed at which it's traveling, the state of the traffic lights ahead, and much more. However, it doesn't need to know what song is playing on the car's radio. That's irrelevant to driving. Similarly, when we're building our model, we must be discerning, selecting only those features that will help the model make accurate predictions. Choosing irrelevant or poor features can lead our model astray, much like adding too much salt to a dessert. Moving on to the algorithm. Once we have our data, how do we process it? This is where algorithms come into play. An algorithm, in simple terms, is a set of instructions that our model follows to learn from data. Drawing back to our Tesla analogy, think of all the complex computations that happen when the car decides to change lanes. The vehicle doesn't just drift over, it uses specific algorithms that factor in speed, distance, and numerous other parameters to make a safe maneuver. Different problems require different algorithms. For predicting stock prices, we might use a different algorithm than for identifying objects in images. It's like the difference between baking bread and making soup. Each requires its own unique method. Next, we have hyperparameters. Every good chef knows that while a recipe provides a guideline, there's always room for some personal touch, maybe a dash more pepper or a tad less sugar. In machine learning, hyperparameters are these little adjustments. In the context of our Tesla example, consider the car's sensitivity to nearby objects. How close does another car need to be before Tesla takes evasive action? Too close and it might be dangerous, too far and it might be overly cautious. Adjusting these sensitivities is akin to tweaking hyperparameters in machine learning. They allow us to optimize the model, ensuring it's neither too aggressive nor too passive in its learning. Lastly, we reach the loss function. Once our model starts making predictions, we need a way to measure how accurate these predictions are. It's the feedback loop, telling us if our model is on the right track or if it needs improvement. Think of a Tesla navigating a tricky parking spot. As it maneuvers, it's continually assessing its position relative to the surrounding cars. Each tiny adjustment gets it closer to the optimal parking position. In machine learning, our loss function helps us understand how far our model's predictions are from the actual results. The aim? Reduce this gap or loss, refining the model to get as close to the truth as possible. First, let's discuss guided learning. Imagine teaching a child to identify animals. You show a picture of a dog and say, "This is a dog." Over time, with enough examples, the child learns to recognize dogs. In the realm of machine learning, guided learning operates similarly. We provide the system with known data and we guide it towards the correct answers. The computer essentially learns from labeled data. Now consider Tesla's vehicles. To ensure their autopilot feature recognizes a stop sign, Tesla might feed thousands of images of stop signs, teaching the system this is a stop sign. Over time, the vehicle gets adept at identifying stop signs in various conditions, rain, fog, night, and so on. It's like a student continuously learning with a teacher constantly providing the right answers. Moving on, we have self-guided learning. Here, it's all about exploration. Imagine leaving a child in a room filled with different toys. Over time, they might group the toys based on color, size, or function, even without you explicitly teaching them. Similarly, in self-guided learning, the computer is given data but not the answers. It finds patterns and relationships on its own. Tesla, for instance, might use this to group driver behaviors. Perhaps the system realizes some drivers prefer faster acceleration while others prioritize energy efficiency. These insights can then be used to customize driving experiences or inform future car designs. It's about discerning patterns without any prior labeling or guidance. Lastly, there's feedback-based learning. Picture teaching someone to ride a bike. They try, they wobble, they might fall, but with each attempt they learn, adjust, and improve. In this category, machines learn through interaction. They make a decision, see the outcome, and adjust based on feedback. Tesla's self-driving features benefit immensely from this. As a Tesla car navigates the roads, it's continually learning. If a particular maneuver leads to hard braking, the system recognizes the outcome as undesirable and adjusts its strategy for future decisions. It's an ongoing cycle of action, feedback, and refinement. Machine learning is not just one size fits all. It offers multiple pathways, each unique and powerful. Whether it's guiding with answers, letting the system explore on its own, or refining through feedback, each method has its merits, and as we see with companies like Tesla, harnessing these approaches can lead to groundbreaking innovations and smarter systems. I'll be guiding you through two core pillars of machine learning, supervised and unsupervised learning. Imagine these as two distinct teaching methods we use to train our machines. Let's begin with supervised learning. Picture it as teaching a student with a detailed guidebook where every question has a known answer. Our main goal here is to predict specific outcomes. It's all about guiding the machine using known answers. Data requirement. For this, we need labeled data. Think of it as a textbook with both questions and answers. Our machine studies this and learns the patterns. Common tasks. Under supervised learning, we have classification, like determining if an email is spam or not. Regression. Predicting a continuous value, like the future price of a stock. Examples. Real-world examples include diagnosing diseases using labeled medical images or predicting stock prices based on historical data. Now, unsupervised learning is a bit like giving a puzzle to our student without showing them the final picture. It's about exploration. The main aim here is to discover inherent patterns and structures within data without any predefined labels. Data requirement. This method requires unlabeled data. It's like handing over a mix of different coins and asking our student, or machine, to sort them. Common tasks. Clustering, grouping similar items. Imagine clustering customers based on shopping habits. Association, finding relationships. If someone buys bread, they might also buy butter. Examples. In real life, businesses use this to segment their market or for recommendation systems, like suggesting songs on a music platform. To sum up, while supervised learning provides our machines with clear answers to learn from, unsupervised learning allows them to explore and discover on their own. Both methods have unique advantages and are crucial tools in the world of AI. As we progress, understanding when to use each method will be the key to unlocking powerful, data-driven solutions. Regression and classification. These might sound like heavy terms, but with everyday examples and a little help from Tesla, we'll simplify them. Regression. Imagine you're trying to predict the exact weight of a fruit based on its size, not just a ballpark estimate like it's heavy or it's light, but a precise value, say 150 grams. This kind of continuous prediction, where we're attempting to pinpoint a specific value, is called regression. Real-world application, Tesla. Let's bring in Tesla, a name we're all familiar with. Suppose Tesla wanted to predict the range of their next electric car based on battery size. They aren't merely classifying the car's range as short or long. They want to determine how many miles exactly. This prediction, say 320 miles on a full charge, is an application of regression. Importance. The power of regression lies in its precision. Businesses, researchers, and industries utilize it for forecasting sales, predicting weather temperatures, or, as in Tesla's case, optimizing product features for consumer needs. Recap. So, every time you're trying to nail down an exact value or amount based on certain parameters, like estimating a car's mileage based on its fuel, you're venturing into the territory of regression. Moving on to classification, think of it as sorting. If you had a basket of fruits and you sorted them into apples, bananas, and oranges, you're classifying them. You're not predicting a value. You're placing each fruit into its rightful category. That's classification. Real-world application. Tesla. Now let's circle back to Tesla. Imagine Tesla's self-driving system. It needs to recognize objects on the road. Is that a pedestrian, another car, or a traffic light? The system isn't predicting a value, it's categorizing or classifying objects to make driving decisions. That's classification in action. Importance. Classification helps in making distinct, clear-cut decisions. It's vital for tasks like email filters, distinguishing between spam and genuine messages, or medical tests determining positive or negative results. Recap. In essence, classification is about placing data into predefined buckets or labels, ensuring clarity and distinction in decision-making. To wrap things up within machine learning, regression is your go-to when you need precision in predicting values, like predicting how far a Tesla can drive on a full charge. Classification assists when you need clarity in categorizing data, just as Tesla's self-driving system identifies objects on the road. Always remember, it's a choice between determining value versus identifying category. Armed with this understanding, you'll better appreciate the AI-driven tools and systems around us. Let's delve into the CRISP-DM process, a roadmap that guides us in transforming raw data into meaningful insights and actionable solutions. CRISP-DM stands for Cross-Industry Standard Process for Data Mining. Think of it as a recipe for successful data projects. Here's a brief walkthrough. Understanding, setting the stage. Picture Tesla's ambition to create a cutting-edge, energy-efficient car. This isn't merely about extending battery life. It encapsulates efficiency across varying driving conditions, terrains, and climates. The product manager's role. Product managers liaise across departments, translating this business goal into actionable technical requirements. By defining success and setting benchmarks, they initiate the data-driven journey. Data understanding. Tesla's wealth of data. Tesla's cars, functioning as smart entities, generate a plethora of data every second. From battery metrics, GPS details, to user preferences and sensor data, the information pool is vast. Sifting through. The challenge lies in finding actionable insights within this sea of data. How does ambient temperature impact battery efficiency? Does highway driving conserve more energy than urban commutes? Data preparation, cleaning. The raw data, while abundant, isn't always pristine. Anomalies like sensor malfunctions or transient software glitches need to be identified and cleaned. Structuring. Post-cleaning. The data is organized in a coherent structure conducive to analysis. For instance, data could be categorized by car model, geographical region, or specific performance metrics. Modeling, foundation, and blueprint. Tesla's existing models serve as a foundational blueprint. By understanding historical data and past performance, a roadmap for innovation is laid out. Incorporating cutting-edge techniques. Being at the forefront of tech, Tesla often incorporates the latest AI methods. Merging the foundational knowledge with these new techniques often leads to groundbreaking innovations. Prototyping and testing. Innovative models, before large-scale implementation, undergo rigorous testing, be it through limited rollouts, simulations, or controlled environments. The robustness of new models is ensured. Evaluation, setting benchmarks. Benchmarking is vital. Expected outcomes like energy savings or performance enhancements are laid out. Real-world versus predicted outcomes. Models, while performing optimally in controlled settings, face the litmus test in real-world conditions. Adjustments and refinements. Post-evaluation, insights might emerge that necessitate model tweaking. It's a continuous dance of prediction, evaluation, and refinement. Deployment, integration. Challenges. Deployment isn't merely technical. If Tesla pioneers a new energy optimization algorithm, seamless integration with existing vehicles is a logistical challenge. Over-the-air updates are a pivotal solution. Monitoring. Post-deployment, the real test begins. How are the new systems holding up in the diverse conditions they're subjected to? Feedback loop. As user feedback pours in, continuous refinement becomes a cornerstone. This loop of deploy, feedback, and enhance is unending. Iterative nature and product management insights. Embracing iteration. CRISP-DM's cyclic nature ensures models are dynamic. As the market evolves, so does the model. Real-world relevance. Given the fast-paced evolution of tech and automotive landscapes, staying adaptive is key. As new insights emerge, looping back and refining becomes essential. The product manager's edge. This iterative process is a boon for product managers. By understanding and embracing this, they can ensure the product's continual evolution, keeping it relevant and pioneering in the market. Every time you hear about a new breakthrough in AI or machine learning, at its core is a model. Models are like the brains behind these systems, making sense of data and predicting outcomes. Today, we'll journey through the making of these models and explore how Tesla's product managers leverage them for strategic decisions. Historical data. What it is. Historical data is a record of past events. For our example, think about Tesla's vast troves of data from their cars on the road, data on battery usage, mileage, driver behavior, and more. This is their gold mine. Why it matters. This past data is essential because it contains patterns. Just as past sales prices can reveal trends in the real estate market, Tesla's historical data can uncover insights about vehicle performance or driver preferences. Training phase. An analogy. Picture a student learning mathematics. They start with simple problems, learn the concepts, and gradually tackle more complex problems. Similarly, a predictive model is trained using simple data sets before it's exposed to more intricate ones. Tesla's training. For Tesla, this could mean training a model to predict battery efficiency based on simple parameters like temperature and driving speed. As the model learns, it might move on to more complex scenarios, maybe predicting efficiency based on combinations of factors like temperature, speed, terrain, and driving style. Model equation, decoding the equation. Once trained, our model has an equation or formula. This isn't your typical algebraic equation, but a representation of patterns and relationships the model has learned. Uncertainty and real-world application. Every equation has a degree of uncertainty. For Tesla, while the model might predict that a car can go 300 miles on a full charge, real-world conditions might alter this. The equation gives Tesla a ballpark, a starting point. New data, the continuous learning. Models aren't static. As new data comes in, they adjust and refine. For Tesla, every new car model or software update provides a stream of fresh data. This data is fed back into the model, refining its predictions. Predictions and adjustments. Let's say Tesla launches a new feature. The initial model prediction could be based on test drives and simulations. But once real drivers use it, new data emerges, leading to model refinements. Outcome: the model in action. Armed with a trained model and fresh data, outcomes or predictions are generated. If Tesla wants to introduce a new supercharger, the model can predict how it'll impact battery life or charging times based on historical data and the new supercharger's specifications. Relevance for decisions. These outcomes aren't just numbers. They guide decisions, inform strategies, and can even lead to innovative breakthroughs. Role of product managers and benefits. Bridging the gap. Tesla's product managers act as bridges. On one side, you have these complex models, and on the other, tangible products and features that customers use. They translate model predictions into product enhancements. Strategic decisions. Let's say a model predicts a 10% increase in battery efficiency with a new update. A product manager can then decide the rollout strategy, pricing adjustments, or even marketing campaigns based on this. Feedback and iteration. Product managers also feed back into the model development process. They bring customer feedback, market trends, and business goals to the table, ensuring models stay aligned with Tesla's broader objectives. Continuous improvement. In essence, for Tesla's product managers, these predictive models are invaluable tools. They provide a roadmap for continuous improvement, innovation, and maintaining a competitive edge in the market. In the ever-evolving landscape of technology and automotive sectors, understanding the model development flow is pivotal. For companies like Tesla, it's not just about making cars, it's about harnessing data, predicting the future, and continuously innovating. And for the product managers steering this ship, this knowledge is their compass. When we talk about machine learning, we often come across a myriad of techniques, algorithms, and models. One such foundational technique is decision trees. Today we'll explore decision trees, their significance, and dive deep into how Tesla's product managers might harness their power. What are decision trees? Imagine a flow chart that helps you decide what to wear based on the weather. If it's sunny, maybe a t-shirt. If it's raining, perhaps an umbrella and a raincoat. This flow chart makes decisions based on certain criteria. Decision trees work in a similar way but in more complex scenarios. Anatomy of decision trees. Nodes. These are points where decisions are made or criteria are checked. Using our example, one node might check if an individual's income exceeds a certain amount. Branches. Paths leading from one decision node to another or to a conclusion. For instance, if income exceeds a threshold, the branch might lead to the next criteria, say credit score. Leaves. These are the final outcomes or decisions. In our loan example, the leaves would be grant loan or do not grant loan. Applications at Tesla. Given the data-driven nature of Tesla, decision trees find various applications. Battery optimization. Consider a scenario where Tesla wants to optimize battery usage based on different driving conditions. A decision tree might look at conditions like outside temperature, driving speed, and terrain to adjust battery usage dynamically. Autopilot decisions. Tesla's autopilot feature could utilize decision trees to make instantaneous driving decisions. For example, if the car detects a pedestrian and another vehicle ahead, it decides the best course of action based on multiple criteria. Benefits for product managers. Simplicity. Decision trees are graphical and intuitive. For product managers, this means they can visualize complex decisions, making them easier to understand and communicate to non-technical stakeholders. Versatility. They can be used for both classification, categorizing data, and regression, predicting values. So, whether Tesla's product managers are classifying vehicle types or predicting sales numbers, decision trees are versatile tools in their arsenal. Rapid decision making. Given their structured nature, decision trees can quickly arrive at decisions. This speed is crucial for real-time applications like Tesla's self-driving functionalities. Informed product development. By visualizing and understanding the decision-making process, product managers can fine-tune product features. If a decision tree frequently indicates battery drain on uphill drives, it signals a need for battery optimization in such scenarios. Real-world example: Tesla's product managers. Imagine a scenario where Tesla wants to roll out a new feature that adjusts car settings based on driver preferences. A decision tree might be used to determine these settings. The tree could begin by checking the outside temperature. If it's cold, maybe the seat warmers are activated. If the driver usually listens to rock music during evening drives, the car might autoplay their favorite rock playlist. As the car learns more about the driver, the decision tree becomes more intricate, leading to a highly personalized driving experience. Conclusion: in the ever-evolving world of technology, tools like decision trees are invaluable. They simplify complexities, provide clarity, and drive informed decisions. For companies at the forefront of innovation like Tesla, and especially for their product managers, understanding and leveraging such tools can be the key to maintaining their cutting-edge reputation. In the realm of machine learning, sometimes relying on just one model isn't enough. It's akin to seeking a second, third, or even fourth opinion before making a crucial decision. Enter Ensemble Models. Today we'll dissect what Ensemble Models are, their prowess, and elucidate how Tesla's product managers could potentially harness their capabilities. What are Ensemble Models? Ensemble models operate on a simple yet profound principle. The collective wisdom of many often outweighs the knowledge of one. By leveraging multiple models and combining their predictions, ensemble techniques aim for improved accuracy and robustness. Analogy: imagine you're at a talent show and each judge individually votes for a contestant they think should win. Instead of just going by one judge's decision, you consider the majority vote. Ensemble models operate on a similar consensus-based approach, but in the realm of algorithms, applications at Tesla. Given the multifaceted challenges Tesla tackles, ensemble models are especially pertinent. Self-driving systems. While a single model might predict a certain path for the car, combining predictions from multiple models can account for various factors like pedestrian movements, other vehicles, and road conditions. The final decision on the car's movement might then be based on this collective input, ensuring safer and more reliable autopiloting. Battery lifespan predictions. Tesla could deploy ensemble models to predict battery lifespan. One model might use driving patterns to make its prediction, another could use charge-discharge cycles, and yet another might focus on ambient conditions. By aggregating these predictions, Tesla gets a more holistic and accurate battery lifespan estimate. Benefits for product managers. Enhanced accuracy. For product managers, accuracy is paramount. Ensemble models, by virtue of their design, tend to reduce errors, so decisions based on these models' predictions are often more reliable. Diverse perspectives. Just as a team with diverse expertise can provide well-rounded solutions, Ensemble Models offer a blend of perspectives. For a product manager, this means a richer understanding of challenges and more comprehensive solutions. Risk mitigation. Relying on a single model poses risks. What if that model has a blind spot or is biased? Ensembles, by combining multiple models, inherently mitigate such risks. This is crucial for high-stakes decisions like those involved in Tesla's self-driving features. Real-world example: Tesla's product managers. Envision Tesla wanting to introduce a new predictive maintenance feature for their vehicles. Individual models might predict maintenance needs based on factors like mileage, driving style, or geographical location. An ensemble model, however, would combine all these predictions, ensuring that maintenance alerts to drivers are both timely and accurate. For a product manager, this not only ensures customer safety but also enhances user trust and brand loyalty. Conclusion: in an age where precision and innovation are keystones, tools like Ensemble Models stand out. They symbolize collective intelligence, the power of collaboration, and the magic that ensues when diverse perspectives converge. For trailblazing entities like Tesla and, more specifically, their visionary product managers, these models are more than just algorithms. They're strategic allies in the quest for excellence. In our day-to-day lives, we often group similar items together to make sense of them, like organizing books by genre or sorting fruits by type. In the realm of machine learning, there's a similar technique that works behind the scenes to organize vast amounts of data into meaningful clusters. Today we'll delve into clustering and explore its vast implications, especially in the context of a pioneering company like Tesla. What is clustering? Clustering is a technique that finds patterns within data. It groups data points that are similar to each other into distinct clusters without any prior knowledge of these groupings. The objective is simple: maximize the similarity of data within a cluster and maximize the dissimilarity between different clusters. Real-world analogy: imagine you're given a mixed bag of various candies. Without knowing the names or types, you decide to group them by color, shape, or maybe taste. Soon you'll have clusters of candies, sour ones, chocolate-filled, gummy types, and so on. Clustering in machine learning operates similarly, but on a much larger and intricate scale. Applications at Tesla. Given Tesla's innovative pursuits, clustering has several intriguing applications. Customer segmentation. By analyzing the vast data from Tesla car owners, driving patterns, charging habits, feature preferences, Tesla can cluster its customers into distinct segments. This allows for targeted marketing, personalized features, or specialized service offers. Driving patterns. Tesla vehicles, with their plethora of sensors, gather extensive data on driving patterns. Clustering can group these patterns: aggressive drivers, cautious drivers, highway cruisers, city navigators, which can be pivotal in refining Tesla's self-driving algorithms. Battery usage profiles. Tesla can cluster vehicles based on battery usage. There might be clusters of cars frequently doing long journeys and requiring fast charging, while another cluster might represent city cars with short trips and frequent charging intervals. Benefits for product managers as data-driven decisions. With clustering, product managers have a clear view of distinct user groups and their behaviors. This can guide decisions on feature rollouts, updates, or even new product lines. Targeted marketing. Understanding customer clusters allows for more focused marketing campaigns. Instead of a one-size-fits-all approach, Tesla can tailor promotions and offers to specific segments, enhancing conversion rates. Enhanced user experience. By understanding and catering to distinct clusters, product managers can ensure a more personalized and efficient user experience. For instance, a Tesla car's software might adapt differently to a user frequently driving long distances versus a city commuter. Real-world example: Tesla's product managers. Consider Tesla's expansive supercharger network. Through clustering, Tesla might identify a segment of users frequently taking intercity routes and heavily relying on superchargers. Recognizing this cluster, product managers could strategize on placing more superchargers along popular intercity routes, offer specialized charging packages, or even introduce features optimizing battery usage for such long drives. Conclusion: clustering, in essence, is the art of finding hidden patterns. In a world inundated with data, it offers a lens to view this data coherently and extract meaning. For dynamic companies like Tesla, and especially for their intuitive product managers, clustering is not just a tool, it's a compass guiding the journey from raw data to impactful decisions. In the world of machine learning and AI, deploying a model is just the beginning of its journey. Once out in the real world, these models need regular care, akin to how a newly launched car model would require periodic checks and upgrades. Today, we'll delve deep into how we manage deployed models and shed light on its significance for product managers at Tesla. Continuous monitoring. Picture a brand new Tesla car rolling off the assembly line. It's been tested, but how it performs in real-world conditions is key. Similarly, after deploying a machine learning model, its real test begins. Continuous monitoring is about keeping a close eye on this real-world performance. It was Tesla application. Consider Tesla's self-driving feature. The underlying models are constantly monitored in real time. If an unexpected behavior is detected, it serves as an early warning to refine the model. Feedback loop. Just as drivers provide feedback on a car's performance, users and systems provide feedback on a model. This feedback is invaluable. It's the bridge between theoretical predictions and practical implications. Tesla application. Tesla cars are equipped with sensors that provide a continuous stream of data. This data, in essence, is feedback on how the car and its features are performing, assisting product managers in understanding user experience and model efficiency. Model retraining. Using our car analogy, over time, wear and tear demand parts to be replaced or upgraded. Similarly, as new data emerges, models need to be retrained to stay relevant. And Tesla application. As road conditions, driving patterns, and even global climates change, Tesla's models adapt by integrating this new data, ensuring that features like autopilot remain state-of-the-art. Version control. Just as software has versions, so do machine learning models. Every tweak, refinement, or major change results in a new version. It's essential to track these versions systematically. Tesla application. Tesla's frequent software updates might include refined versions of their machine learning models, ensuring customers always have access to the latest and safest driving features, performance metrics. In any endeavor, knowing your success criteria is crucial. For models, performance metrics are these criteria. They provide quantitative measures of the model's efficiency, accuracy, and overall performance. Tesla application. When Tesla rolls out a new feature, be it self-driving or predictive maintenance, they would have set metrics to evaluate success. This could range from accuracy in predictions to user satisfaction scores, stakeholder communication. Effective communication bridges the gap between technical teams and decision makers. By keeping stakeholders informed, you ensure alignment, support, and proactive problem solving. Tesla application. If a deployed model detects a potential widespread issue in Tesla cars, immediate communication to stakeholders can lead to swift action, be it a recall, software patch, or public communication. Role of product managers, on benefits. Overseeing the model lifecycle. For Tesla's product managers, overseeing the full lifecycle of a model is vital. From its deployment to eventual refinement or replacement, they ensure the model serves its purpose efficiently. Informed decision-making. The insights from managing deployed models guide product strategy. If a model predicts a surge in demand for a particular car feature, it can lead to production changes or marketing campaigns. Risk management. By actively managing models, product managers mitigate risks. Early detection of issues ensures brand integrity and user safety. Conclusion. In the grand orchestra of machine learning at Tesla, while models might be the musicians, managing them post-deployment is the conductor, ensuring the symphony plays harmoniously. For product managers, understanding this is pivotal, turning data-driven insights into tangible products and meaningful user experiences. That's it for today's course, folks. If you found this content valuable, please give it a thumbs up and don't forget to subscribe for more insights. See you in the next one.